The aim of the experiment is to determine viscosity of the given liquid by capillary flow method, that is Poiseuille's flow method. We will see what are the apparatus that are required. We need a burette which is graduated, and then a rubber tubing to connect the burette to a capillary tube. This is the capillary tube, and a wooden plank which can rest the capillary tube. We also need an iron stand for supporting the burette. A stop clock, a razor stopwatch, which you have already used in torsion pendulum. You also need a meter scale. At first I will explain the experiment without filling the water. Hypothetically, we will imagine that water is filled in the burette, and I will explain the whole experiment. Then we will fill the water and see how the water should fall. We have to fill water in the burette up to a particular mark, preferably up to 0, and see that water flows through the capillary tube in drops. That is, we have to ensure that the motion of the water is streamlined motion. You can keep a tray or a beaker on the other side and see if the water is falling in drops. That is why we are using a capillary tube. After that, what we have to do is, we have to find out how much time it takes for a particular amount of water to flow through the capillary tube. In our case, we are fixing the value as 5 cc's. So if we start, for example, at 40 cc's, then we have to find what is the time taken for flowing from 40 to 45, 45 to 50, 50 to 55, etc. This is what we are going to do in the experiment. So the principle here is, you know, the height of 40 from the axis of the capillary tube is different, height of 45 from the axis of capillary tube is different, etc. So we are actually calculating time for 5 cc flow of liquid, but you know height of 40 and 45 are different. So when we calculate the time, what height have we to take? Whether we take the height of 40 from axis of capillary tube or height of 40 from height of 45 from the axis of capillary tube, we have to take the average height. That is, we have to take the height of 40 from the axis of the capillary tube and height of 45 from the axis of the capillary tube. They are respectively named as H1 and H2. So you have to add them both and divide by 2. That is, the average height will be H1 plus H2 by 2. Since we are taking average height here, your values will be accurate always when the distance between the 40 cc and 45 cc is as small as possible. For example, we are taking 5 cc's here. Had you taken 2 cc's, it will be closer together and your average height will be much better. But we have also to note the time conveniently. So optimum value of 5 cc's has been fixed for this experiment. So accordingly you can do the values. I will show you later how to take the height of the respective graduations from the axis of the capillary tube. So what is happening when you adjust for streamlined motion now is, the time taken for a given volume of liquid to flow through the capillary tube is going to depend on the pressure head between the two ends of the capillary tube, that is this side and that side. So when the height of the column keeps on decreasing, because when the water starts flowing down, the height of the liquid also starts coming down, that is, the height of the liquid column decreases. So what will happen when the height decreases? The pressure difference also decreases. Hence the time taken will be more. As the liquid column goes down, the height of the liquid column decreases, and hence the pressure difference decreases, and hence more time will be taken for the liquid to flow through the capillary tube. This is a schematic diagram of the instrument I already showed you. You can see a stand, then the burette, and then it's connected to the capillary tube placed on a wooden plank, and then we have a beaker to collect the water. Remember, we have to ensure that the capillary tube is perfectly horizontal. You can't keep it sliding like this or like this. It has to be perfectly horizontal. You have to ensure that before the experiment. You also have to ensure that there is no leakage in the tube or the capillary tube. So here you can see the burette graduated. You can see the height has, an example is shown, 5 cc, and then you have 10 cc. You can see axis of the capillary tube. From the axis of the capillary tube, the height of 5 is h1, the height of 10 cc is h2. So the average height will be h1 plus h2 divided by 2. So we will now see what is the formula for viscosity of the given liquid. The viscosity of the given liquid is given as eta equal to pi rho g a power 4 by 8 lv into h into t, Newton second meter power minus 2. See that there is an a power 4 in the numerator. So this has to be very accurate, but this value will be given to you in the laboratory. You can ask the lab assistant for the value of the radius of the capillary tube. We'll now see the explanation of the symbols. Rho is the density of the given liquid in kilogram per meter cube. Most often we use only water, so the density is going to be 1000 kilograms per meter cube. G is the acceleration due to gravity in meter per second square. A is the average inner radius of the capillary tube in meters. It is the average inner radius of the capillary tube, mind you, because we are also going to take one outer radius later on. H, small h, which is mentioned there, is the average height or pressure head of the liquid column in meters. This I have already told you is h1 plus h2 divided by 2, depending on the range what we are taking. T is the time taken for V meter cubed of liquid to flow, that is in seconds. In our case, we take 5 cc of the liquid, or 5 into 10 power minus 6 meter cubed of the liquid. L is the length of the capillary tube, that is what the length which has gone into the tube also. It has to be from this end to that end, the whole length of the capillary tube. Sometimes what people do is they don't take the length of the capillary tube which has gone into the rubber tubing. You have to take the whole length of the capillary tube. And V, of course, is the volume of the given liquid in meter cube, and that is of course 5 cc. Let us now see how to do the experiment. As I told you earlier, we need to pour water into the burette. Ensure the burette is also vertical and the capillary tube is horizontal, and the flow of the liquid is in drops, that is streamlined motion is there. So once the water comes to the 40 mark, you have to start the stop clock or the stopwatch. When it comes to 45, don't press stop, because we need time continuously at 40, 45, 50, 55, etc. Now don't press stop. Press the button which is split reset. You can see the watch has stopped running, but internally it will be running. For you it looks as though the watch has frozen at this particular point. This is to note time conveniently when the water meniscus has come to 45. So what you do is note this time. For example, here this is only a hypothetical one, this may not be actual. Here it is 17.58 seconds. So note this in the observation. Here 40 is the starting time, we have already indicated it as 0. At 45, note the time. This is trial 1, note this particular time, what is there in the watch. After noting, again press the split reset. You can see it was 17.58, but now it has started at 1 point something. So internally it was running, but for you to note down, it was convenient because we use the split reset button for this. So again when it comes to 50, what you do, again press split reset button. Again it will stop. Again note down the value for 50. Note down the value for 50. Then again press split reset button. When it comes to 55, again stop. Again note down. Like this, repeat the readings up to 70 cc for every 5 cc fall in height. When it comes to 70, you can either press split reset or you can finally press stop itself. Okay, let's assume it is at 65 now and it's going to 70. So for the last reading, you may press stop. Note down the reading, and then when you reset, it will go back to 0. So this way you can conveniently note down the time. As in torsion pendulum, note the time up to microseconds. So like this, again pour the water for the second trial. Don't disturb anything in the instrument, because if you take out the burette and then do something and pour the water, the height will change. So don't do any changes in the apparatus. Keep it as it is, just only pour water for the second trial and repeat the experiment. We have to now see how to take the height of the 40 cc, 45 cc, etc. and write down. For that, have a meter scale and we'll see how to do that. Let us see how to measure the height of the different graduations from the axis of the capillary tube. I remove this capillary from here because we want it from the bottom of the capillary tube. Keep the 40 mark like this. You can use a scale or a pencil. Now I don't have a full meter scale, so I am using only one small one. But when you use a full meter scale, the height will come up to the 40 mark. This is the 40 mark. So what you do is height of 40. Height of 40 can be measured when you use the full scale. It's enough if you measure just the height of 40 first from this bottom of the capillary tube. What we are doing is, actually we are measuring the height from the bottom surface of the capillary tube. After measuring 40's height, all you need to do is measure height of 5 cc. Example, here you can see, if I take the height of 5 cc, this is the 40 mark and this is the 45 mark. So from 40 to 45, the height is 2.5 centimeters. So if the height of 40 mark from the base of the capillary tube is 45 centimeters, then what will be the height of 45? It will simply be 45 minus 2.5 centimeters. So you have to note that value in these columns, that is the range is fixed, that is in flowing from 40 to 45, you have to note the initial height. Height of 40 I have already told you is 40 centimeters from the base of the capillary tube, 45 centimeters from the base of the capillary tube, and then subtract 2.5. Height of 45, that is H2, will be 45 minus that 2.5 centimeters. So you don't need to keep noting the height for all the values. So 45's height automatically becomes 45 minus 2.5 here, that value you can note down. 50's height will be 45 minus 5. So that is 40. It will just be 40 centimeters. Like this you can keep noting the heights up to 70 cc value. Now what we need is not the value from the base of the capillary tube, it is the axis of the capillary tube we are interested in. So that we have to actually take into account here. So what we do for that is, take the capillary tube, use a screw gauge, find the outer diameter. Once you find the outer diameter, half of that will be the radius. So find the outer diameter of this using the screw gauge. So half that will give you radius, that is H prime. So outer radius of the capillary tube will be given here, that is H prime. Once you have that, you know you have measured from the base. So from the base you have measured the value. So if you subtract the radius of this outer radius of the capillary tube, you will get the height from the axis of the capillary tube. So note that H prime in centimeters here, what you get in screw gauge will be in millimeters, mind you. convert it to centimeters and write it here. Then average height h will be h1 plus h2 divided by 2 minus this h prime. You know the time taken for flowing from 40 to 45 from your previous tabulation. So you can note down the time here. So you know the height, average height, you know the time of flow. So what will this be? H into T in centimeters second, or you can directly convert it into meters second and also write it. So after doing that, take the average value of H into T and you will get that in meter second. From the value of the given radius of the capillary tube, that is inner radius of the capillary tube, you can compute the value of viscosity. As usual, we will tabulate data for calculations. The data for calculation is recorded like this: density of the liquid rho, average inner radius of the capillary tube A is given to you, length of capillary tube is measured by you, average value of H into T is from the tabulation, acceleration due to gravity G is 9.8 meter per second square, volume of the given liquid is V equal to 5 into 10 power minus 6 meter cube. Outer radius of the capillary tube H prime is written here. If you want you can write this, otherwise in the tabulation itself you can finish it off. So now substitute all the values and do the calculation. Remember, when you do the calculation you have a power 4. As usual, don't do power of 10 in the calculator. Have it separately. So find eta, and the approximate value we will get is somewhere around 8 into 10 power minus 4 Newton second meter per minus 2. Remember, the value at 20 degrees centigrade is only 1 into 10 power minus 3. For a higher temperature, viscosity will reduce. As temperature increases, viscosity reduces. So depending on the temperature in the lab, the value of viscosity may change. And depending on the quality of water you are using, the viscosity may change. We will just see a sample set of reading as usual. You can see here burette reading is already listed for you, and the starting time is already being listed as 0. So T1 is the starting time is 0, and we have blocked this. At 45, as usual, I told you use the split time in the razor watch and record the timing when it comes to 45. Now here the split timing, the microsecond is not being written. You have to write up to microseconds, though it is not indicated here. As in torsion pendulum, you have to indicate the timing at 45 up to microseconds. I'll repeat, when it comes to 45, you need to press split in the stopwatch and note the time, and then again press split. So it will start running. When it comes to 50, note the time, etc. up to 70. You can see how to do 2 trials. Take the average. The timing also has been written. What calculation has to be done also is given directly here. You just need to follow up the calculation. That is from 40 to 45, the timing is this. 45 to 50, this is the time taken, etc. Okay. So one thing you will note is, as you keep going down, since the pressure head reduces, the time starts increasing. You can see time taken for every 5 cc to flow goes on increasing. Please observe the pattern here. Now we will see how to do the rest of the calculations. The outer radius of the capillary tube measured using a screw gauge has been listed here as 0.279 centimeters. Have it in centimeters itself. Finally you can convert everything to meters. So from the previous tabulation, you have the value of time, that is 40 to 45. The time taken for liquid to flow is 95 seconds. So the initial height is 47.1, final height is 44.5. Similarly, height of 45, you can see 44.5, that is H2 initially, now it becomes H1. So minus the height of 5 cc, you will get 41.9. Like this up to 70, you have to fill the columns. So you have the time of flow from the previous tabulation. So we have H here, T here, multiply these 2 columns and you get the last column. So take the average of all this and write it down here. So some burettes may not be marked up to 100, you may have only 0 to 50. In that case, you can start your values from 20 cc. So as told earlier, do the calculations, note down all the values in the data for calculations, compute the values, and you get the final answer like this. Now this value is slightly high, but it doesn't matter. You can see now that I have poured water and it has started flowing down. Note that the water is flowing in drops through the capillary tube, but still we cannot start because it is still not maintained the streamlined motion. You can see the drops are falling quite fast. That is why we wait when it comes to 40. That is, we wait up till it comes to a level of 40, so that the water gains the streamlined motion. It should not be a turbulent one. So this is how you should adjust. You can see there should not be any constriction between in the tube what goes to the capillary tube. It should be a free flow of water. So this is how you can see. Now you can see it when it starts coming, the height of the liquid starts reducing. The flow is more or less drop by drop. You should ensure this before you start. You should also ensure there is no leakage when the water is flowing in between. The tube should not leak. So if there is something like this, first itself report to the attender. Secondly, as usual, as in torsion pendulum, check the stopwatch, mainly whether the split reset button is working, because that is what is important in this experiment. So I start pressing stop, it starts running. Next I press split reset, it has to stop when I press the split. Again when I press split, it should start running. And then again when I press split, it should stop. So verify before starting the experiment. Don't start doing and say in between the watch is not working.